In this problem, we're given a circuit diagram here, and we need to use the node voltage method to find V1 in the circuit shown. We're actually going to use the node voltage method with dependent sources because of the position of our current right here. And then we have the steps that we're going to follow to actually do this right here. It's a little bit simpler. So first we're going to need to define two nodes. Our first nodes that I'm going to define are this one and this one. You kind of want them in the meat of the circuit analysis, so in the middle part. At node 1, we're going to have V1 minus our voltage source. So we will have our V1 minus the voltage source here, which is 60 because this is the source voltage, and since the voltage is going across this 2 ohm resistor and then splitting into this V1 resistor, it's going to have to be subtracted. Looking at node 1, we have voltage 1 minus our voltage source, and for this example this holds true because we have our V1 right here. So we want to get the voltage that goes across this resistor right here. That means the first resistor is going to be 2. So we have our V1 minus 60, and this is because the voltage going across this resistor, since this resistor and this resistor are in series, is going to be split, and that's why we have to subtract 60 from the V1. Next we have V1 plus R1, and this is just going this way. Next we have V1 minus V2 over the resistor between them. Our V2 is going to be this V2 right here. They have to be in parallel like this. So we're going to have a plus and then V1 minus V2 over our 3 ohm resistor. And that is going to be this resistor right here, not this one. And the reason why it's V1 minus V2 is because our V1 is going down, as we stated here. However, our V2 will be going in this way. And for Kirchhoff's current law, all currents going into a node, which holds true for this one as well, is going to be a negative. And then it is equal to 0. So this is our first equation. I'm going to simplify this by multiplying the entire equation by 24. If we do that, we're going to get this, and then we can further simplify this by combining like terms. And if we do that, we will get this as our final equation. Now we're going to look at the node at 2, and that node at 2 is V2 minus our V1. It's basically this, but it's kind of reversed because we were looking at the other node right here. Our V2 will be going out, and our V1 would be going in like this, so that's why it's negative, and it is over the resistor between them, which is 3 ohms. Sort of similar to this situation right here. And then this is being added to V2 over R2 because we have our voltage 2 going out, and our R2 is just the 3 ohms that is with it. So I'm going to associate this with a blue highlight like this. And lastly, we have the V2 minus our current. And this is because we are dealing with the node voltage method with dependent sources. And this is over the last resistor. The last resistor being this 3 ohm resistor right here. So we'll have a plus and then the 3 ohm resistor right here. And on top of it, we would normally have a V2 minus I. However, since our current is going to be going like this, down this way, and it can go like this, we are just going to have a negative 6 I naught because that's what our current is. It's not going through our V2, it's just going this way. And then this is equal to 0 as well. To simplify this, we are just going to multiply everything by 3. If we do this, we can then simplify it again and get a negative V1 plus a 2 V2 minus a 6 I naught. And this is equal to 0. So this is our next equation. For our first equation, we can modify this a little bit. We can scoot the right side over, and this just plus a 0 I naught, so it stays consistent with this next part. In step 4, we need to see that we have an I naught equal to our V1 minus V2 over the resistor between them. I'll do this in gray. So we're going to have I naught is equal to our V1 minus V2, two unknowns, over our resistor between them, which is 3. After we do this, we're going to multiply both sides by 3, and then we are going to subtract 3 I naught from this side. If we do that, we are going to get V1 minus V2 minus 3 I naught is equal to 0. And that is our formula for this part. From here, if we look at our three equations, our top part has a 21 V1 minus an 8 V2 plus 0 I naught, and that's equal to 72. So that means we really only have a V1 and a V2 in here. Well, if we look at these bottom two, if we can somehow cancel out the I naught, we're just going to be left with a V1 and V2. And if we're just left with a V1 and V2, we can set one of them equal to each other and plug this into our original equation to find V1. So to cancel out the I naught on the bottom, I'm going to multiply the bottom part by -2 and then add them together. If I do that, we're going to get this, so we can cancel out the I naughts, and then we are just going to be left with a -3 V1 plus 4 V2, and that is equal to 0. We can set this equal, and we'll set V2 equal to our equation. That way we can plug this in and solve for V1. So we will have V2 is equal to a 3 V1 over 4. And this is our last equation. We're going to plug it into this main equation right here. And if we do that, we're going to get this. So our 0 is 0. And then this we can simplify to be 2. And then we're going to have a 21 V1 minus 6 V1 is equal to 720. And then if we subtract this again, we are going to get a 15 V1 is equal to 720. And then if we divide this out, we are going to get that V1 is equal to 48 volts. So this is the voltage for V1, and this is our answer. For more videos like this one, there will be a playlist linked below. There will also be notes linked below that would help with this problem and other intro to circuit analysis problems.